Welcome back to Statistics. I'm Dr. Jeff Groh. Today we're going to begin our discussion with tests between two proportions. In this case, we don't have one population that we're sampling from. We perhaps have two populations that we're sampling from. They could have different sample sizes. As an example, we may wish to determine the preference for, say, a particular soft drink in one state versus another state. You take a sample from one state and a sample from the other state, and you determine the preference for that particular soft drink. Is there a difference between the preferences in the different states? Well, we can do that with a test between these two proportions. Samples 1 and 2 have different data. There's x1 and x2. We can treat these as success responses versus the sample size, however you determine what success is. And these different things give us proportion 1 and proportion 2. You calculate these by taking x1 divided by n1, that gives you proportion 1, and x2 divided by n2 gives you proportion 2. At the outset, we have no reason to believe that there is a difference between these proportions until we can demonstrate otherwise. So we will calculate what is called a pooled proportion. The pooled proportion will be denoted by P bar, and it will be all of the successes divided by all of the sample size from both samples. What is the null hypothesis under one of these tests? It can be that the proportions are equal, but it doesn't have to be. It could be that the proportions have some specified difference. There's a known difference between them. We are going to require that each of these has at least 5 successes and at least 5 failures as well. But that would be n1 minus x1 and n2 minus x2. That's the number of failures. At least 5 successes and 5 failures, and the samples are simple random samples. What is the test statistic? It will be a z-score, and it's going to be calculated in a special way. We're hypothesizing that there's some difference, some null hypothesis difference between the proportions. This could be 0 if we assume that the proportions are equal. But it doesn't have to be 0. It can be whatever the null hypothesis proportional difference is. To calculate the standard error here, we're going to use that pooled proportion and its complement q hat, q bar, divided by n1. And then the same thing divided by n2. That's where the square root ends. That's where the fraction goes. And then we'll conduct this the same way as we have in the past, using either a p-value or critical z's, or even the confidence interval method. One of those 3 methods we'll use to conduct the hypothesis test. We'll use a slightly different formula for this standard error when we calculate confidence intervals. For confidence intervals, we don't know what the difference in the proportions is. The best that we can do is take the sample difference plus some standard error, a margin of error, versus the sample difference minus the margin of error. How is the margin of error calculated? Much as we calculated these confidence intervals in the past, we'll take these critical z's, dividing the alpha on each tail, times the standard error. The standard errors here are calculated a little bit differently than we wrote down before for hypothesis testing. In this case, we'll use the actual proportions from the data like this. For example, the county clerk wishes to know whether mailed out reminders will improve voter registration. A random sample of 1,250 voters are separated into experimental and control groups of 625 each. So N1 and N2 are 625. In group 1, 295 out of the 625 registered with no reminder. What about group 2? 350 of 625 registered with a reminder. Our null hypothesis will be that there is no difference. P1 minus P2 is 0. 0 is the specified difference. Our alternative hypothesis will be that if you didn't get a reminder, fewer will register. So the proportion 1 will be smaller than proportion 2. Let me write down the data here. X1 is 295. N2 is 625. X2 is 350. So there's a 55 difference between these two. There is a difference in these two samples, but is it statistically significant? We'll have to do a test to find out. Let's do this a couple different ways. First, let's try it the old-fashioned way of just calculating the z statistic. P1 hat will be 295 divided by 625, and P2 hat will be 350 divided by 625. Remember, the sample statistic here is going to be P1 hat minus P2 hat minus the null hypothesis difference, which in our case is 0. We need to calculate the pooled probability of success, and that's going to be 295 plus 350 divided by 1250. Once we've calculated that, we'll divide by this pooled P bar Q bar divided by N1 plus P bar Q bar divided by N2. And that will complete the calculation. So for the pooled probability of success, 295 plus 350 divided by 1250. I'm getting 0.516. That means that Q bar, which is 1 minus that, I'll store this, by the way, this in a memory location on my calculator. Here we get 0.484. The test statistic, crunching the numbers, make sure you put parentheses around the top here. I'll have 295 divided by 625 minus 350 divided by 625, close parentheses, divided by second square root A times B times 2 divided by 625. The test statistic is negative 3.11, more than 3 standard deviations below the mean. That's a good indication that the null hypothesis is probably false, or at least that we should reject the null hypothesis. What is the critical z? Which reminds me that I forgot to set my level of significance. Let's suppose the level of significance is 0.05 or 5%. We can find the critical z using the inverse normal. Second distribution, inverse normal. The area is 0.05, and we want to do this on the right. And the critical z is 1.645. Well, negative 1.645 if we're doing a left-tailed test. So here's our z alpha, the critical z, at negative 1.645. The z that we calculated is way over here at negative 3.11. We're definitely in the critical region, and therefore we reject the null hypothesis. It seems that we have statistically significant evidence then that these mailers do in fact increase voter registration. We could have conducted this whole thing using the test for two proportions built into the calculator. We'll go to Stat, Tests, and we need the two proportion z-test right here. The x1 is 295, n1 625, The x2 is 350 into 625. We're testing to see if P1 is less than P2. The statistic, the z-score that we get is negative 3.11, just as before. Check out this p-value, 9.26 times 10 to the negative 4. That's a really tiny number, 0.000926. That's certainly less than 1%, and therefore we reject the null hypothesis. This means that we reject the null hypothesis. We have statistically significant evidence to show that the proportion from sample 1 is less than the proportion from sample 2. In our next example, based on an internet survey, 78 out of 100 American adults claim that they are willing to donate a loved one's organs after death. However, a random sample showed only 20 out of 100. Is there a difference? Use alpha equals 0.01. Our null hypothesis is P1 equals P2. 78% versus 20% seems like a very significant difference. However, it's entirely possible that these differences can be explained by random chance from the sampling process. Let's use as our alternative hypothesis that P1 is greater than P2. We'll go to Stat, Tests, and then the two proportion z-test. In this case, x1 is 78, n1 is 100, x2 is 20, n1 is 100. And this time, we're testing to see if P1 is greater than P2. Note that the z-score here is 8.2. That's way out in the tail, a very improbable event. And how improbable? That's given by the p-score, the p-value here, which is 1.2 times 10 to the negative 16. 10 to the negative 16. That's a decimal point, 15 zeros, and then the 1. So this is extraordinarily tiny, and we will most assuredly reject the null hypothesis. And so we reject the null hypothesis. In a test of the efficacy of echinacea, which is an herb that is sometimes used to treat colds or flus, 40 of 45 subjects treated with echinacea developed the cold? A rhinovirus. In a placebo group, (88 of 103) developed a cold. Use alpha equals 0.05 to test the claim that echinacea can help prevent you from getting the cold. So the null hypothesis is that the proportions are the same. The alternative hypothesis will be proportion 1 is less than proportion 2. So the proportion getting the cold, taking echinacea, is less than the proportion who did not take echinacea. We'll go to Stat, Tests, and 2 proportion z-test. In this case, x1 is 40 out of 45 for n1. x2 is 88 out of 103. We're testing to see if P1 is less than P2. Notice that the z-score is 0.56 and the p-value is 0.71, which is definitely bigger than our level of significance. So in this case, we fail to reject the null hypothesis. And therefore, we fail to reject the null hypothesis. We did not find statistically significant evidence of a difference in the proportion of individuals getting the cold using echinacea. We're next going to study the differences between means with 2 samples. In this case, we're going to deal with independent samples. We'll have a mean 1 and a mean 2. The null hypothesis will be mean 1 minus mean 2 is some specified difference. And of course, there are 3 possible alternative hypotheses. The test statistic will be a t-score. We'll have the measured difference in the means from the sample versus the null hypothesis difference. And for our standard error, we'll have s1 squared over n1 plus s2 squared over n2. We'll have variances from each of the samples divided by their sample sizes added together under the square root. T-scores require a degrees of freedom. We'll have this be the smaller of n1 minus 1 or n2 minus 1. I should note that technology uses a complicated formula for the degrees of freedom. If the population standard deviations are known, then you can use a z-score. if you make the assumption that the standard deviations for the populations are the same, then you can use a t-score where you'll have a pooled variance and the degrees of freedom will take n1 plus n2, 2. What is this pooled variance? The pooled variance takes n1 minus 1 s1 squared, n2 minus 1 s2 squared, divided by n1 plus n2 minus 2. As an example, suppose that 2 bikes are being tested. To see if one gives a shorter commute time. There's bike 1 versus bike 2. And 26 trips with bike 2. The mean commute time with the first one was 107.8 minutes, whereas the mean with the second one was 108.4 minutes. What about the standard deviations? S1 was 4.9 minutes. S2 was 6.3 minutes. We'll use a level of significance of 0.05. The null hypothesis will be that the means are equal, and the alternative hypothesis will be that the means are different. In our calculators, we'll use a 2-sample t-test. We press Stat, Tests. This is a 2-sample t-test. We're entering statistics. X1 is 107.8, where the standard deviation for the first sample was 4.9. Sample size was 30. X2, the second mean, was 108.4. Standard deviation there was 6.9, and the number there was 26. In this test, we're testing to see if there is a difference one way or the other, and we are not going to use a pooled variance. The t-statistic is negative 0.37, which is not very big at all, and the p-value is 0.71, which is huge. We will fail to reject the null hypothesis. Notice the complicated degrees of freedom in this case. The technology is using a very complicated formula for the degrees of freedom. We're next going to look at matched pairs. There are many cases where data can be paired, such as before versus after sorts of studies, or tests between twins. When using paired data, We'll assume the data has maybe one value for one of the pairs and another value for the other of the matched pairs. They come in these pairs, and we'll pair them using an ordered pair like this. We'll use these differences. We'll have a mean difference as our null hypothesis. It might be that the mean difference is 0, or the mean difference is some specified value. We'll also have a sample mean difference. We'll have a standard deviation for the sample differences as well. The statistic that we'll have is a t-statistic. It will be our sample mean difference minus the null hypothesis mean difference divided by the standard deviation of the mean differences divided by the square root of the sample size, and the degrees of freedom will be n-1. As an example, a team of heart surgeons at a particular hospital believe patients are anxious and may benefit from counseling. Heart patients are tested for anxiety. Before and after counseling. So there's a natural pairing, the same person before versus after. How anxious were they before counseling? How anxious were they after counseling? So we're going to make a table. Patient and before versus after using some test scores. Jan had a 121 and then 76. Tom, 93 and then 93. Diane, 105 and then 64. So she seems to have chilled out after counseling. Barbara, 115, 117. Counseling did not seem to help Barb. Mike, 130 versus 82. Bill, 98 versus 80. Frank, 142 versus 79. Carol, 118 versus 67. And then Alice, 125 versus 89. Did counseling make a difference? Well, there are certainly differences apparent here, but are those differences statistically significant? We'll enter the differences manually into a list. so that we can calculate the mean and standard deviation. 121 minus 76 is 45. 0. What is this one going to be? 41. Negative 2. Yep, if it's negative, you have to make it negative. This is going to be what? 48 and 18. 63. We get 51 and 36.
I'll enter the data as a list. I'm going to edit. I've already entered this list of all of these differences, as you can see here. So we're going to go back and look at StatCalc, and we're going to do one variable statistics using list 1. The things that we need here are the standard deviation and the mean. The mean difference was 33.33333 and so on, and then the standard deviation was about 22.9. So we're going to use these in our formula. 33.333 whatever divided by 22.9 divided by the square root of the sample size, and that gives us a t-score of 4.37, which is pretty large. To calculate the p-value, we can use the inverse t. We'll look at second distribution, inverse t. The area is, we're using a level of significance here of 0.01, so I'll use 0.99. The area to the left, the degrees of freedom is 1 less than the sample size, so that's 8. And so our critical t is 2.896. The t that we have is way beyond the critical t.
The conclusion is that we reject the null hypothesis being that the mean difference is 0, and it looks like we have statistically significant evidence to show that the treatment does reduce anxiety.